journey further out continues as we head towards Jupiter. However, as we approach the gas giant, our focus changes to one of its 75 moons, Ganymede. Ganymede is Jupiter's largest moon. It has a magnetic field and experiences auroras. In 1996, it was also discovered to have a thin oxygen atmosphere, though it is too thin to support life. However, it is not the planet's surface we have come here to see.
A 2015 study shows that Ganymede's magnetic field undergoes a distinct lack of rocking. In other words, something is stabilizing the magnetic field, and it was theorized that this was likely the result of a subsurface saltwater ocean that spans the entire moon. Also, you see the surface is covered in 40% dark and 60% light grooved areas, which is the likely result of tectonic activity and liquid water seeping up from beneath the ice, which further supports the idea of a subsurface ocean.
What kind of life might exist here? Well, to answer that question, we can look to one of the most inhospitable environments on Earth, Antarctica. Whilst Antarctica is home to many unique creatures, to be analogous to Ganymede, we are not interested in the frozen landscape of the world's driest continent, but what lies beneath. So we must drill down to see what is trapped deep beneath the glaciers, subsurface lakes.
Water has some peculiar properties. Importantly, well, for us, is that it expands as it freezes, meaning that enormous pressures can actually stop water from freezing as it can't expand. So, in places like Antarctica, under the weight of enormous amounts of ice, you can find liquid water in the form of lakes and oceans deep down. Since the first was discovered in 1970, 379 subglacial lakes have been identified and mapped in Antarctica. Most of these were identified through RES or radio echo soundings carried out by either aeroplane or satellite. These lakes can get big. The largest is 240 kilometers long, 50 kilometers wide and several hundred meters deep. For comparison, Sydney Harbour is only a few kilometers wide at most and on average is only 13 meters deep. In more recent years, we've even been able to drill down to a few of these lakes and take samples. For example, a 2019 study found animal carcasses belonging to things like krill, as well as living bacteria. The animals themselves probably lived some 10 or 100,000 years ago during warmer periods in Earth's climate. And then, as the weather cooled, they got trapped in there by advancing glaciers. However, there was enough organic material left for the bacteria to survive this entire time. Yet, this has nothing on the next example, which is one of my favorites, blood falls. The blood comes from a lake 400 meters beneath the ice that was enclosed some 1.5 to 2 million years ago. The lake itself isn't actually red. The color comes from iron in the water rusting or oxidizing as it comes into contact with our atmosphere. These fantastic ferrous falls are an incredible way for scientists to sample the subglacial lake without having to drill down and possibly disrupt the ecosystem that has remained isolated for so long. Instead, they can simply sample the water as it comes out, and sample it they have. Extensive studies of this blood water has identified 17 unique microorganisms that inhabit this subglacial lake. Somehow life has survived this long, and isotope analysis, or basically the weighing of different atoms, suggests how. These microorganisms appear to be modifying sulfur, but unlike some life at hydrothermal vents, they're not using it to obtain energy. Instead, they're likely metabolizing some leftover organic material. Instead, they seem to be using sulfur compounds to breathe with iron from the underlying bedrock, which makes these organisms probably the greatest metalheads on Earth. Oh, come on, I'm allowed to tell a chemistry joke periodically. I'll let myself out.
University of California scientist Slavek Tulizin said about blood falls, A place like this would probably be as close of an analogy as we can find on this planet for sub-permafrost life habitats on Mars. However, it may also provide a glimpse as to what life in many subsurface oceans might look like. Which brings us back around to Ganymede once more, and its subsurface ocean. What are the chances that life might exist here?
Well, very slim at best. You see, Ganymede's oceans are about 10 times deeper than the deepest parts of Earth's oceans, meaning that the pressure at the bottom is absolutely immense. But you see, whilst we might have liquid water and possibly some organic chemicals, we need to consider the last criteria for life, an energy source, or at least some kind of chemical circulation that gives our aliens something to metabolize. And for places like Ganymede, this would most likely come from underwater volcanoes, hydrothermal vents, or something that at least resembles them. However, under the immense pressures of Ganymede's oceans, these would likely freeze over, stopping any chemicals or energy being pumped into the ocean. So, unfortunately, no life. However, liquid water is still surprisingly common in our solar system, and we're nowhere near done yet looking for it. So, with that, to infinity and beyond! Or, well, just to the next moon over.
Our trip through the solar system moves on once more. Though, this time, we don't have to go far before we find another place that could harbor life. Io is the most volcanically active body in the entire solar system. Its eruptions are so violent and impressive that they can be seen from Earth with a telescope. Eruptions from the planet's surface have been observed to reach 300 kilometers from the planet's surface, big enough to directly take out some of the satellites orbiting Earth.
Io definitely fulfills the energy criteria for life, but at a little bigger than our own moon, where's it getting it from? You might suspect that it's getting its energy in a similar way to Earth, radioactive decay in the object's core. However, this isn't enough. Instead, it's getting it from gravitational interactions with Jupiter. You see, on Earth, as the moon goes round us, it creates tides by moving the water around. In fact, a similar thing is happening on Io, except instead of moving water around, it's moving the entire planet. Uneven gravitational attraction causes the object to bulge and then bounce back. All of this creates immense heating, which gives us our lovely volcanoes. Once more, what does this mean for life? Well, on Io, fortunately probably not much. I know, you might be getting bored of me saying that, but as of yet we don't really have any evidence for liquid water here, and the surface temperature, due to its very thin atmosphere, is minus 143 degrees Celsius, so we're unlikely to find any life, or at least life as we know it. Oh, and if that wasn't bad enough, this is also not to mention that Io gets bombarded by immense amounts of radiation from Jupiter. But there is a promising note here, because this mechanism for generating heat is a fairly generic one. So if we could find other environments where a more tempered version of this is going on, we might find a place more suitable for life. So let's carry on.
Staying in orbit around Jupiter, we come to probably the most likely place to find life around this gas giant. As we approach a small gray moon, slightly smaller than our own, its surface crisscrossed by fractures, and most promisingly, we can see thin jets of water reaching into the emptiness of space, clear evidence of liquid water below the surface. We have now arrived at Europa.
Like Ganymede, Europa gets energy through gravitational interactions. It's tidally locked to Jupiter and takes 3.5 days to complete an orbit of the planet. Also, tidal forces may help with chemical mixing in any subsurface ocean. Our first close look of the moon came in the 1990s with the Galileo spacecraft. but evidence for liquid water wasn't forthcoming. Though, more recent observations with the Hubble telescope and reanalysis of the Galileo data suggests that there might be plumes of water ejecting some 160 kilometers from the planet's surface. Then, in 2019, we hit the jackpot with these plumes being directly observed by the Keck Observatory in Hawaii using an IR spectrograph, proving that there is liquid water on Europa. On top of that, recent computer modelling suggests that there has been and still could be active underwater volcanoes, which would provide both the chemicals and energy necessary to support life. It is predicted that this ocean resides 15 to 25 kilometers below the surface, and probably reaches depths of between 60 to 150 kilometers, making this one impressive body of water that would give Europa twice the amount of water by mass than you could find on Earth. It is suspected by some that Europa is the most likely of Jupiter's moons to house life. So to get a closer look, NASA plans to send the Clipper probe, which will give us better measurements of the moon's gravity, magnetic field, the depth of the crust, and the makeup of the surface, just to name a few things. This will not only give us a better understanding of the chemical composition on Europa, but anomalies in the gravitational and magnetic fields may enable scientists to identify the presence of subsurface volcanic activity. Clipper is planned to be launched aboard a Falcon Heavy rocket in 2024, where it'll eventually reach Europa by 2030. Now, whilst this might be quite a few years away, who knows what discoveries are out there waiting to be made.
So far, we have looked at a number of Jupiter's moons. But what about the planet itself? The gas giant alone contains more than 2 times the mass of the rest of the planets in our solar system combined, composed mainly of hydrogen, H2, and helium, He. Along with its enormous size comes enormous storms. The famous red spot being a storm more than twice the size of Earth, that has lasted for hundreds of years. So, once again, we ask ourselves, where can we find life?
Just like Venus, Jupiter could support life in its atmosphere, which is why we're going to make a brief stop here. Recent studies have supported this hypothesis and have also claimed that Venus would not have enough available water to support life, but Jupiter does. Scientists at the University of Belfast have noted that at the right atmospheric layers, conditions should be favourable enough for life. It was also mentioned that it's not the volume but the concentration of water that should be considered here, and they argue that Jupiter has enough of this. But unfortunately, sending probes to Jupiter's atmosphere is extremely difficult, so even if there is life there, it'd be almost impossible to detect with current technology. But who knows, it's still an interesting side note. But once again, we keep going on our journey for life.
And with that, we leave Jupiter behind and venture further out into the darkness. Although we are moving even further away from the sun's heat, we're not yet moving away from the possibility of life. Just like Jupiter, Saturn also has some interesting moons to visit. Specifically, let's just look at 2 of them, the first being one of the most likely places we are to find alien life in the solar system, Enceladus. This little moon is 680 times smaller than Earth, about the same diameter as the state of Arizona, and is the most reflective body in the entire solar system. This incredible albedo means that it has a surface temperature of only negative 200 degrees Celsius, negative 330 Fahrenheit. But once more, we can't judge a book by its cover. We must dig a little bit deeper.
Unlike the other moons on this list, we have a fairly decent understanding of what chemicals might be present on Enceladus, thanks to Cassini. As the probe approached the environment around Saturn, it began picking up particles, which is not very surprising on its own, given that Saturn's rings are mainly made up of solid chunks of various sizes. What was surprising was the composition. You see, the rings of the Saturnine environment are mainly made up of rock ice, so water, but these particles seem to contain a lot of chemicals that were mainly silicon-based, or in particular silica, or SiO2. So what's up with that? Scientists soon worked out that these particles were coming from Enceladus, and Cassini was soon directed to get a closer look. And what a look it got! As it closed in, Cassini grabbed some amazing images of Enceladus, showing a faint halo of dust and the impressive water jets ejecting subsurface ocean material into space, some of which was ending up in Saturn's ring system. Particles in these jets are reaching speeds of 400 meters per second and are erupting from cracks in the moon's south pole known as the tiger stripes.
Cassini was able to get some awesome close-up photos of Enceladus as well, but the probe wasn't done yet. Probably one of the biggest highlights of the Cassini mission came on the 28th of October 2015, when Cassini was able to pass directly through one of the geyser plumes and directly sample some of the chemicals therein. Cassini was able to identify hydrogen gas, H2, which was great evidence for hydrothermal activity and could be a good energy source for life. More silicon particles were detected, along with organic carbons such as methane, propane, acetylene, and formaldehyde, plus inorganic salts and biologically available nitrogen. All this suggests volcanic activity and a particular process known as serpentinization, which is basically a rock-water interaction, are taking place.
So, what does this tell us? Well, it tells us that Enceladus' subsurface ocean is probably a lot closer to the surface than the other moons we've looked at, being maybe about 10 kilometers below the surface and reaching depths of 20 to 40 kilometers, so that we won't actually have any problems like we saw on Ganymede. Also, the composition of this ocean seems to be salty and basic, which, yes, Earth's oceans are acidic, but this would give Enceladus conditions similar to Earth's soda lakes. Soda environments like Lake Mono is home to a great biodiversity of microorganisms, so this is definitely not a factor against finding life on Enceladus. A paper published in Nature has suggested that Methanothermococcus okinawensis, a methanogen archaea that converts H2 and CO2 into methane, could survive in the conditions found on Enceladus. Here on Earth, these microbes inhabit hydrothermal vents that are likely undergoing very similar chemical processes to what can be found deep in Enceladus' oceans. Now, the paper does conclude it's unlikely we will find life exactly like this given Earth's unique evolutionary history, but it does provide a window into what alien life might, at least in part, look like, or the sort of chemical processes that might keep it alive, which I just find so amazing. However, once again, I must temper the excitement with some realism. Now, whilst Enceladus does have all three ingredients that we've already mentioned for finding life, liquid medium, chemicals, and an energy source, we may not have enough variety in the chemicals. You see, to have life, it is suggested you need a minimum seed set. This is basically where enough variety in the chemicals that are present exists to allow the basic building blocks of life to form and the more complex chemical reactions to start. And computer modeling suggests that Enceladus does not meet this minimum seed requirement. Though this time we don't have to end on a negative. Whilst we may not have found this minimum seed set, we are not done looking. The Enceladus Life Finder, or ELF, is a mission concept by NASA to land a probe and directly drill through the ice to look for signs of life. Now, yes, the decade-long Cassini mission around Saturn may have ended, but humanity's search for answers definitely has not.
After our trip through the plumes of Enceladus, we come round to the second largest moon in the solar system, Titan. No, Titan. Whilst Titan is suspected of having a subsurface ocean, like many of the other moons, here we are going to judge a book by its cover. For you see, on Titan you can find clouds,
it rains, and the surface is also home to rivers, lakes, and seas. It has a thick atmosphere, being the only moon in our solar system to have one. However, things are not as they seem because the surface is still cold at minus 179 degrees Celsius. The atmosphere is mainly made of nitrogen, N2, with no oxygen, and the lakes and rivers are made up of hydrocarbons like methane and ethane.
If I was to stand on the surface of Titan, with of course an appropriate spacesuit, then I would find that the rain falls a sixth of the speed that it does on Earth, and also for those who like their numbers, the droplets would be about 50% larger. Now, this might all be interesting, but why are we here? If we've already covered moons with better examples of subsurface oceans and Titan is so cold, what's the moon got to offer? Well, basically, life as we don't know it.
But I've always been fascinated by that phrase, life as we know it. I have a feeling that we may encounter life as we don't know it.
Titan's seas, some of which are hundreds of meters deep and hundreds of kilometers wide, provides a liquid medium for life to exist, and the rain and other processes show there is a way to mix chemicals and provide energy. A team of engineers one day decided to take a break from studying semiconductors and instead model a cell system for methane-based oxygen-free life. Because why the hell not? The team came up with a chemical structure that would act as a cell membrane in liquid nitrogen conditions, which they named an azotosome. This chemical structure would allow for life to survive in very, very different chemistry to what is found on Earth, and might provide a mechanism for life and cells to exist on Titan, which I think makes for some incredibly amazing future discoveries. We also have other places on Titan that might host life as well. For example, meteorite impact sites could stay warm for hundreds of years, warm enough for water-based organic chemistry to occur, though personally I think this is a less likely scenario to give us life due to time constraints. However, a place that might be more likely to host life than this is pockets of water ammonia mixes some 200 kilometers below the surface before we reach any subsurface oceans. These pockets remain liquid basically because the ammonia is acting as antifreeze, and it has been hypothesized life could exist in these liquid pockets as well. To put the icing on the cake, when the sun becomes a red giant and blasts Earth dry with radiation, Titan will get a bit warmer. It will reach probably a balmy minus 70 degrees. Now, whilst this might sound cold, it is warm enough for water ammonia mixes to exist on the surface as a liquid. And just as we previously mentioned, this is an environment that could possibly host life. And with that, we come to the end of our look around the moons of Saturn. Now, not just a lot of the information, but the photos I showed as well, all comes from the Cassini probe. And so I'd like to end this section by playing a clip from NASA outlining how the mission ended.
On the final orbit, Cassini will plunge into Saturn, fighting to keep its antenna pointed at Earth as it transmits its farewell. In the skies of Saturn, the journey ends, as Cassini becomes part of the planet itself.
By now, we begin to drift further into the dark, cold reaches of our solar system. Whilst Uranus and Neptune are expected to have some moons with subsurface liquid environments, we might be reaching the outer reaches for the possibility of life, as energy gets harder and harder to find. Or so we thought. Pluto, the ruler of the underworld, was probably the last place many people expected to find liquid water with no major source of energy keeping it warm. However, in July of 2015, all of this changed.
The famous dwarf planet is only about 2/3 the width of our own moon, or about half the width of the USA. Pluto's also so far out that it's part of the Kuiper Belt and takes 248 years to complete a single orbit. Yet, despite its size, it has 5 of its own moons. However, the largest of which, Charon, is so big that the two orbit each other in a dance that is more like a binary planet system than a moon orbiting a planet. However, beyond this, it was hard to really tell anything about Pluto because it was just too far away to see in detail. Sunlight takes 5.5 hours to reach the dwarf planet, and a patch of ground on Pluto receives only 1/1600th the energy the same patch of ground would receive if it was on Earth. In other words, it's cold. Really cold, at -379 to -396 degrees. Yet, the solar system wasn't done proving that this is not necessarily a limiting factor to find life. In 2015, the New Horizons probe passed close to Pluto after nearly a decade-long journey to the outer reaches of our solar system. As the probe got closer, it sent back increasingly detailed photos of the dwarf planet, as seen here. And when it got close enough, it revealed a heart-shaped area the size of Texas that was dubbed Sputnik Planitia by Japanese scientists. This white-coloured basin is an area of Pluto where the ice shell is incredibly thin and there exists a subsurface sea that should have frozen long ago, but hasn't. Now, you might think that like Titan you could have an ammonia-water mix, but this was ruled out pretty quickly as Pluto's composition is only expected to be 1% ammonia, not the 30% that would be required. Instead, the likely culprit is methane. Methane is released by chemical cracking in the still hot core. The methane gets trapped by ice, forming cage-like structures known as calthrate or gas hydrates. Now, nitrogen would not be trapped by this and probably escapes, which would account for Pluto's thin blue atmosphere. The trapped methane then acts as an insulating layer that has kept this subsea ocean liquid for much longer than would otherwise be expected. And the formation of calthrate hydrates has been proposed as a generic mechanism that may allow liquid bodies of water to exist on many objects in the Kuiper Belt and beyond. So it's quite likely Pluto is not the only place out this far that has liquid mediums on it, which is quite cool and extends our concept of the Goldilocks zone, where it was originally thought a planet would need to be to have liquid water, much, much further than we ever originally would have guessed. There is one place left in this solar system that is fairly obvious but yet to be explored in this video: Earth. Could there be alien life here? What do I think of the possibility of some form of alien life possibly existing on Earth? Well, before we get to that answer, I want to take a moment to thank all of those who made this video possible. It is by far the biggest project I've taken on this channel, and I couldn't have done it without all the extra help I got. To start with, I'll thank Jen from Polymathic, who not only helped me with a lot of the information for this video, but also made a lot of the lovely animation you guys have been able to see. Plus, I also want to thank Tessa Fisher, who is an astrobiologist who looked over the script to make sure I didn't stuff any of the science up. Plus, of course, I can't go any further without thanking my two lovely voiceover artists, Kitty and Randolf Richardson. So thanks to you all, plus also special thanks to all my viewers as well, because it is you guys that are the reason I make these videos. If it wasn't for your watch time, if it wasn't for people enjoying these videos and hopefully learning a bit out of it, I wouldn't be able to do it. So thank you all, and with that, let's return home. Earth, the only place we know life exists, yet in this vast universe, certainly not the only one. Now, I want to take a moment to first address the idea of intelligent alien life on this planet, or at least visiting this planet. Now, before you get carried away, it was actually videos of supposed alien life that motivated me to make this video.
Roger, they're troubleshooting. Did you box moving target? No, I took an auto track. Oh, okay. Oh my gosh, dude. Wow, look at it fly!
Well, the absolute stupidity of videos like this was what motivated me to make a video based in reality, so there's that. As for the overall concept of what I think about the prospect of intelligent life on this planet, I think Monty Python's Eric Idle put it best when he said,
"And pray that there's intelligent life somewhere up in space, 'cause there's bugger all down here on Earth."
As for microbial life, it doesn't look like we have any visitors either. But panspermia still remains a fairly likely hypothesis for the origins of life on this planet, which is basically the idea that life started somewhere else in the universe and was seeded here long ago, being carried on comets or meteors. Now, this is why it becomes useful to look for life outside of Earth, say in this solar system or in the universe at large. If we find similarities or differences, it actually can enlighten us as to our cosmic origins. Because if we find life that is very similar to that on Earth, it may suggest that in fact life has a more universal origin and it's been spread around the universe at large. Or if life is very different to what we find on Earth, it might suggest something about how easy or how difficult it is for life to arise independently in different environments. Either way, even places like Mars and Venus still give us an insight, as they may have housed life at one point or may have even seeded Earth themselves. So our search will continue, and we're not done today with this video. Hopefully, even though we didn't find any definitive signs of life in our trip through the solar system, it did go some way to showing just how weird, wacky, and wonderfully complex our own backyard is. And so on that, I want to leave you with one final message. Look at the immense differences explored just in the inner part of this solar system alone. From the burning hellscapes of Venus to the freezing landscapes of Pluto. So imagine what differences we could find on a cosmic scale. All this illuminates just how trivial the differences are between humans here on Earth. We are all on this mote of dust, suspended in a sunbeam. We're all part of humanity. We are all in this together. This is our home and the only one we have for now. So we should work towards putting our differences aside and advancing humanity for all those who live or will live on this planet. Whether or not we are alone, our place in the cosmos remains here. Remember, I'm almost a doctor, and until next time, be like a proton. Stay positive.